Hello, honorable judges. We are the Nyquist Knights from the Bangladesh University of Engineering and Technology, and today we present our solution for the IEEE Signal Processing Cup 2026 Phase 2. The core objective of the challenge is to isolate a specific target speaker located at 90 degrees azimuth while effectively suppressing an interference sound located at 40 degrees. This must be done using a sparse 2 microphone array, which is a significant constraint. We approached this problem by dividing it into two distinct tasks. Task 1, which focuses on an ideal anechoic environment, and Task 2, which addresses the much harder challenge of a reverberant environment with multipath reflections. Now, I will give in detailed explanation of the system architecture, algorithm used and design choices, and the overall processing pipeline. So, we start with system overview. I am Rahan Siddiq. Now I will be presenting the system overview. Welcome to the methodology. Our system utilizes a unified deep learning framework called the phase-aware dual path architecture, which we designed to handle both anechoic and reverberant tasks efficiently. The pipeline is end-to-end, converting raw audio into the frequency domain using the SDFT. Crucially, we process the full complex spectrogram, preserving both magnitude and phase. Rather than separating them, the model predicts a complex ratio mask CRM to filter noise, and we reconstruct clean speech via the inverse STFT. This ensures we leverage all spatial cues. Input feature design for inputs. We use a 4-channel tensor where we stack the real and imaginary components of both microphones to explicitly preserve the inter-channel phase difference (IPD). Since sound travel time varies, the IPD acts as a compass, distinguishing the target at 90 degrees from interference at 40 degrees. For task 2, we add a 5th channel called the inter-channel level difference (ILD), which provides robustness against reverb induced phase smearing. Here is our core architecture. Our core DP PCRN architecture follows a modified unit structure. The encoder uses strided convolutions to compress audio into high-level semantic features. The bottleneck models temporal evolution and rhythm. The decoder uses transposed convolutions to restore resolution. We employ skip connections to link the encoder and decoder, preserving the fine-grained spectral details often lost during compression. Now, encoder, decoder, and complex convolutions. Standard networks often ignore phase, so we solve this with complex convolutions. We process real and imaginary parts via cross coupling, where the real output depends on both inputs interacting. This respects sound physics and enables the network to learn rotation invariant filters, effectively learning phase awareness to perform precise beamforming towards the target angle. Bottleneck innovation, dual path RNN. To handle long sequences efficiently, we implemented a dual path RNN DP-RNN in the bottleneck. We slice features into overlapping chunks and process them in 2 stages. First, intra-chunk RNN scans frequency to model local spectral correlations. And second, the inter-chunk RNN scans across time to model long-term sentence structure. We stitch this back using an overlap add method, allowing us to model long sequences with minimal memory footprint. Attention mechanism. We enhanced focus by adding self-attention to the bottleneck. This block computes a similarity matrix across features, asking whether the signal is target speech or noise. It generates a weight map, assigning high values to speech dominant frames and suppressing noise. This acts as a dynamic gate, filtering background noise before decoding. Strategies for task 1 and task 2. We tailored our strategy for the two different tasks. For task one, an echoic environment. The environment is clean with no echoes, so we rely heavily on the phase difference since the path is direct and the cues are very sharp, allowing us to surgically separate the speakers. For task 2, reverberant echoes mirror the phase information. So to handle this, we trained the model using simulated reverb data and added the interchannel level difference or ILD as an extra input feature to help identify the target even when the phase is mazy due to reflections. While the convolutional layers handle spatial and spectral features, the YGRU handles time by tracking how the speech evolves, allowing the model to understand the context of a sentence rather than just individual sounds. Training objectives. For training, we used scale invariant SNR, SISNR. Unlike standard error matrices, SISNR measures alignment quality independent of amplitude. It forces the model to maximize target energy while minimizing residual noise, ensuring the output is mathematically clean and phase aligned. Signal reconstruction. Finally, for reconstruction, our model predicts a complex ratio mask, CRM. We apply this mask via element-wise complex multiplication to the noisy input, which rotates the interference phase to cancel it out. The result is converted back to the time domain using an inverse STFT, delivering a smooth, artifact-free waveform that concludes our methodology. Hello, I am MD Marjul Riyad. Now I will explain implementation details, description of datasets, pre-processing steps, tools and frameworks used, and key implementation aspects. Let's begin with our data generation strategy for task 1. Since this is the baseline task, we simulated a perfect anechoic environment. We utilized clean speech from the LibriVox corpus and noise textures from the Muson corpus. Specifically for every male target speaker, we generated variations mixed with female speech or non-speech noise. The geometry was fixed to a room size of 4.9 by 4.9 by 4.9 meters. To establish a strict baseline for spatial filtering, we generated 16,500 samples, mixed strictly at 0 decibel signal to interference ratio, or SI. This control setup forces the model to learn separation based solely on direct path clues. Let's go to our next slide. Task 2, robust reverberant dataset generation. However, the real world is not anechoic. Task 2 introduces reverberation, which smears the spatial clues we rely on. To build a robust model, we moved to a highly randomized protocol. First, we targeted a reverberation time or RT60 of approximately 0.5 seconds using the image source method with order 5 reflection. This simulates realistic echoes bouncing off walls. Second, we randomized the room dimensions between 4.7 and 5.1 meters and jittered the source angles by plus or minus 5 degrees. Finally, we introduced dynamic mixing. Unlike task 1, we varied the SIR between -3 and +3 decibel. This variability forces the network to learn robust features like interchannel level difference or ILD, which remain reliable even when phase information is degraded by echoes. In our next slide, we will tell about implementation and architecture. Moving on our implementation, we designed our pipeline for low latency execution suitable for mobile devices. We do not just feed the model raw audio, we explicitly calculate spatial features to guide the learning process. For the anechoic task, we use the sine and cosine of the interchannel phase difference or IPT. For the reverberant task, we add the ILD to the input tensor, creating a 5-channel input. These features are processed by two specialized architectures, a dual-path phase-aware convolutional recurrent network for task 1 and a causal CRN for task 2. Crucially, for the reverberant task, our causal CRN uses causal convolution to ensure there is zero look-ahead latency. Satisfying the real-time constraint, both models predict a complex ratio mask or CRM. This allows us to reconstruct the signal phase explicitly rather than just estimating the magnitude, which is vital for high fidelity audio results and performance evaluation. Now I will explain quantitative and qualitative results, performance matrices, comparison with baselines, and discussions of strengths and limitation. First, it's about our visual analysis. Qualitatively, the performance of our system is evident in the visual analysis. On the left, look at the waveforms, specifically the bottom plot, showing the clean versus enhanced overlay. The red line, which is our output, sits tightly on top of the green ground truth line. The tight alignment proves that our complex ratio mask didn't just filter volume, it accurately reconstructed the signal phase, effectively solving the phase smearing problem caused by reverberation. Please go to the next slide for our spectrogram visualization. On the right, in the noisy input at the top, you can see chaotic green smearing, which is the interference masking the target speech. In our enhanced output at the bottom, we have successfully recovered the distinct horizontal harmonic stacks of the targeted voice. Most importantly, we have restored the dark vertical gaps that represent silence between words, proving the interference has been suppressed. So you can see the results. Our approach delivers strong quantitative results. For task 1, the anechoic scenario, we achieved an OSINR of 13.76 decibel and a PESQ score of 3.051. And task 2, despite the severe reverberation, we maintained high intelligibility with an STOI of 0.883 and an OSINR of 8.99 decibel. The Nyquist Knights have developed a robust phase-aware beamforming system that effectively zooms in on sound regardless of acoustic challenges. So in our next slide, we will tell about strengths and limitations. To critically evaluate our system, we have identified key strengths and limitations. Our primary strength is the use of explicit spatial features like IPD and ILD. By feeding these directly to the network, we allow the model to learn directionality much faster than if it had to infer it from raw spectrograms. Another strength is our phase-aware reconstruction. By predicting the real and imaginary components of the mask, we avoid the robotic artifacts common in magnitude-only masking. However, there are limitations. Our model assumes a fixed 2-microphone geometry. If the distance between microphones changes, the spatial features would shift, requiring retraining. Additionally, while accurate, the dual-path RNN bottleneck is computationally heavier than simple CNNs, which is a trade-off we accept for better audio quality.
Hello everyone, my name is Rasul Islam Dibbo and I will be walking you through our system's implementation and code base. Here we are seeing a folder which will be uploaded for our phase 2 submission. In this folder, we are seeing two subfolders. First one is task 1 anechoic and the second one is task 2 reverberant. Both filters contains the same content. So I am going to task 1 anechoic. In this folder, we are seeing a subfolder named dataset and some files. So in the subfolder dataset, if we go into it, this contains all of our raw audio files, including the clear targets, interference profiles, and the raw microphone mixtures. In the dataset folder, there are 5 subfolders containing the audios. The naming sequence is explained in the readme.txt file. So by using or by reading this file, you can understand the naming sequence of this of the files in the folders. So now There are also many files. The first one I want to explain is process task1.m. So this is our master MATLAB script. It acts as the center hub of our system, handling the data loading, metric calculation, and launching our unified dashboard. By using this file, we can generate an enhanced audio from mixed audio files of mic 1 and mic 2. There are inference script 2.py and base.pt files also. So to handle the heavy neural network processing, we decoupled the AI from MATLAB. Inference script 2.py is our Python bridge script. It is called dynamically by MATLAB to load our trained PyTorch model weights stored here in base.pd and execute the speech enhancement. Task1 anechoic. There are another file task1 anechoic 5db.mat. Finally, it contains all the data you have asked to submit. Now I want to explain the process task1.m file. So in this file here, we have to change this path for our data set. So from where we can find the path. So in the submitted folder, there is a folder named dataset. So in the dataset folder, there are 5 subfolders, and if we look at the mixture signal mic 1 subfolder, there is 20 files, and you can select any file path from here, and you have to select the corresponding file from mixture signal mic 2 and target signal also. So after selecting the file paths, the data will be loaded. So after loading the raw audio from the dataset, the very first major step is executing our neural network. Based our end goal for task phase 3 is a deployment on edge device like smartphone. We keep the AI decoupled from the environment or the evaluation environment. We call this call a custom run Python bridge file. So which work it does, what this bridge does is temporarily write the multi-channel noise audio to disk, format a command line trigger for our Python script, and then instantly load the enhanced target speech back into our MATLAB's memory. This ensures our AI model acts exactly as it would in real world. Once we made the enhanced audio, we move to the official metrics calculation. For task 1 anechoic environment, we implemented optimal scaling. As you can see here, we calculated the alpha scalar using the dot product of the clean and enhanced signal. We apply this scalar to the output before computing the matrices. This is a crucial engineering step. It ensures that our OSINR and SISDR matrices evaluate the structural reconstruction of the target speech rather than unfairly penalize the model for slight amplitude shifts. We then calculate the official SPCUP matrices OSINR, SISDR, STIO, and the required VISQOL, which is equivalent to PESQ here. Now let's see the system in action. I will run the process task1.m live script live. So I'm running it. Down here in the command window, you can see MATLAB loading the anechoic dataset and successfully calling the Python neural network bridge. The processing is entirely local and highly efficient, taking a few seconds to process the entire audio sequence and calculate the metrics. And here is our unified evaluation dashboard. We built the dashboard to provide a comprehensive, all-in-one view of our model's performance. So on the left, we have the time domain waveform. At the top is the highly corrupted mic 1 input, mixing the target's speech with 0 dB SIR interference. Below, it is our model's output. If you look closely at the bottom overlaid plot, you can see that our red enhanced signal tightly tracked the green clean reference because we used optimal scaling. Our model correctly recovers the speech structure without suffering from destructive amplitude scaling. At the right side, there is spectrogram. So notice how well the enhanced output preserves the critical speech formats, the horizontal bands of energy, while successfully suppressing the broadband interference and competing speakers that were present in the mixture. There is the matrix panel. Visually, it looks great, but our matrix provides its robustness mathematically. For this specific 0 dB SRO and 5 dB SNR anechoic scenario, our model achieved excellent scores. So here are the scores. The OSINR is 15.38 dB, SISDR is 15.26 dB, PESQ is 3.433 dB, STIO is 0.921 dB. And you can see the improvement here also. So ultimately, audiovisual zooming is about the user experience. So let's listen to the difference. First, I am playing the noisy signal here. So here is the noisy signal.
Tanto como yo de él, mi contenido.
Suddenly up to 100 degrees.
Now I am playing the enhanced output of our model.
Tanto como yo de él, mi cantemida.
Okay, now I am playing the clean audio.
Tanto como yo de él, mi cantemida.
So here you are seeing the result. So that's all for task 1, and task 2 for task 2 all the files are saved as same approach for we explained for task 1. So thank you very much for staying with me.